GCSE question of the week, week 12, part 2, the higher tier question. So the graph shows the velocity of a particle. So remember, velocity just means the vector quantity speed with the direction given. Okay, so we've got the velocity of a particle, velocity in meters per second because it's speed, and time in seconds on the x-axis. Describe how you would calculate the acceleration of the particle at 1.5 seconds. Okay, so what do we know about acceleration? Well, we know that acceleration is the change in velocity divided by the time. It's the rate of change of velocity. Okay, where v is the final velocity and u is the initial velocity. So v minus u is just the change in velocity, and we divide that by time. Okay, so if we find the change in velocity and divide it by the time, we know that's going to be the acceleration. But what's the change in velocity in this graph? Well, the change in velocity is the difference in the y-axis, and the change in the time is the difference in the x-axis. So really we're talking about the change in the up divided by the change in the across, and we know what that is. That's the gradient. So to find the acceleration on a velocity time graph, we need the gradient of the graph. Okay, so where do we find the gradient of the graph? Well, it says 1.5 seconds. So 1.5 seconds is here. So at 1.5 seconds, we need to find our gradient. The trouble is this is a curve, so we don't have a straight line. We can't just directly use y equals mx plus c. So we need to draw a tangent at that point. So we're going to draw a tangent, a straight line, at that point, exactly at 1.5 seconds, something like that. Okay, and that's going to give us the instantaneous acceleration, because every point on this curve, the acceleration is changing. So we want it here, it's called the instantaneous acceleration. So I think I've drawn a neater one. And there's a neater straight line at the point 1.5. So we really need to find the gradient of that line. That's going to give us the acceleration. So the gradient is this change divided by this change. We're going to be careful with our scale. I reckon every little 2 squares is worth 1 by the looks of it. We've got 1, 2, 3, 4, 5. So each 2 small squares is worth 1. So I reckon that value there is 12. That's 4 squares above the 10. And this value down here is 1. So our change in y is 12 minus 1, that's 11. And we're going to divide that by the change in x, the change in the time, and that's 4 seconds. So we've got 11 over 4. It's not seconds, idiot. Okay, we've got 11 over 4. That's 11 meters per second divided by 4 seconds. So we've got 11, let's put one big one. 11 meters per second divided by 4 seconds. That's going to give us, it's a calculator paper, so we're okay. We could do this one in our head, but 2.75. Okay, so we've got 2.75. And what about the units? We've got 2 choices. We can either work them out, or we can know, well, this is acceleration. We know acceleration is meters per second squared. Okay, but the units here are telling us. They're telling us we've got meters per second divided by another second. Another unit of seconds. We've got meters per second divided by another seconds, or meters per second divided by another seconds. That gives us meters per second, or meters per second squared. Okay, so we've got 2.75 meters per second squared. 2.75 meters per second squared. Number 2, estimate the distance travelled by the particle during the first 4 seconds of its motion. Well, this time we want the distance travelled. Now, again, from physics, you might just know, oh, it's the area under the graph, or you might need to have some understanding of why that is. So, what do we know about velocity? Well, we know that velocity is the rate of change of displacement. Okay, well, that really just means the rate of change of distance if we're talking about one direction. So we've got distance divided by time, and then really velocity will become speed if we're just forcing ourselves to think in one direction. So velocity is distance divided by time. Okay, we rearrange that, we get distance equals velocity, or really speed, times time. Okay, so the distance is the velocity times the time, and we want the distance travelled by this particle. So it's the velocity times the time. So imagine for a minute I have a graph, velocity, time, that does something like this. Then the distance is the velocity times the time. Well, the velocity is that, and the times that. If we multiply them together, we get the area under the graph. Okay, so what about if it's a triangle shape? Well, here, if that's velocity and that's time, okay, the velocity times the time. Well, time's easy, it's that distance. I mean, distance along the axis, obviously. So it's that time. And velocity, well, this time we could find the average velocity. The average velocity, because the velocity is always changing here. The average velocity is halfway up that axis. So that would be half times the velocity times the time. Oh, that would give us the area of this triangle. So again, this is going to work out that half times the velocity, the maximum velocity times the time, will give us the area under this triangle. So it kind of makes sense that the area under one of these velocity time graphs is going to give us the distance. But again, because we've got a curve here, that makes things slightly trickier. We don't have a straight line that we could split into a triangle and a rectangle, or we could just do one trapezium for that whole area. We've got something a bit more complicated. So what we need to do is we need to split this curve into some different shapes, and we're going to use trapezia. So we're going to take this point and this point, and we're going to say that, well, that curved line there is almost, not quite, but almost a straight line. So the area under that part of the curve is represented by this trapezium. And if we do the same thing here, that's almost straight. So we could get a nice estimation of the area under it by that trapezium. And we could do the same thing here, almost straight, and we get a third trapezium. And again here, almost straight, we get a fourth trapezium. That's going to give us a much better estimate than if we'd have just said, well, let's pretend it's that shape. You can see that my approximation is much closer to the actual curve. So we've split it into four areas. All we need to do now is work out the area of those four trapezia. So again, I've got a slightly neater one here. Go with some proper straight lines. We know our area of a trapezium rule. It's area equals half a plus b multiplied by the height. But remember, a plus b in this are the parallel sides. So in that first trapezium, this is a, and this is b. And h, okay, even though it represents height, is the perpendicular distance between that a and b. So that's our height. So we need to make sure we've got that right each time. After that, we can work out 1, 2, 3, 4, the area of each of those trapezia. So let's do area 1. Right, area 1. We're going to get half times a plus b. Well, again, I've got to look at my scale carefully. I think that's 3, and I think that's 4. So we've got half 3 plus 4 times height, and the height is just 1 second. It's 1 across, so that bit's easy. Okay, so that gives me half of 7. That gives me half of 7 multiplied by 1, just got 3.5. And what are our units this time? Well, we know that we're working out a distance, and we know we've got meters per second, so these have got to be meters. But if you're unsure, what have we done? We've multiplied this time. To find an area, we've multiplied meters per seconds by seconds on the x-axis. Okay, we've got seconds on the top, seconds on the bottom. We just get meters. So definitely got units of meters. All good. Right, number 2. Trapezium 2. We've got area equals half times a plus b. Well, this time we've got 4. And we've got 7. Yep, I think that's pretty much dead on 7. Okay, so we've got half of 4 plus 7. And again, just times 1. Every time difference, time interval between those trapezium lines is going to be 1. So 4 times 4 plus 7, beg your pardon, is 11. We've got half of 11. It's 5.5. 5.5 meters. Right, number 3. We've got area equals half a plus b. Well, this time we've got our 7 and 10, 11, 12. So we've got 7 plus 12 times 1. That gives me half of 19. That's 9.5 meters. And trapezium 4, we've got area equals half of 12. plus, looks like 19, 16, 17, 18, 19 times our height of 1. So 12 plus 19 is 31, so we've got half of 31. It's 15.5. Okay, so we know that the area under those 4 trapezia represents the distance travelled, and we know that's going to be the sum of those 4 values we've got above. So we've got 3.5 plus 5.5 plus 9.5 plus 15.5 is going to give us our total distance. Okay, so those 0.5s look like they make 2. This is a calculator paper, but this is not tricky. We've got 19, 24, 29, 32, looks like 34 metres. Okay, so our total distance travelled is 34 metres, and we found that by working out the area under the curve, but it's only an estimate. Let's go back. So we've now got 34 metres, and that's during the first 4 seconds of its motion. Explain whether your answer for the distance is an underestimate or an overestimate. Well, here, if we look back at the lines that we drew, every single approximation line was slightly above the curve. So we're going to get a value for the distance that's slightly above the real value. So hopefully it's clear to you that in this case, we've got an overestimate. So 34 metres is an overestimate because our, what could we say, our trapezia lines were above the curve. Had they been below the curve, then clearly then we'd get an underestimate, a value lower than the real value. Okay? So just to summarise, if you have a velocity time graph and you want the distance travelled, you're going to find the area underneath that line or curve. If you want to work out the acceleration, and in this case the instantaneous acceleration, you need the gradient. So if you want the acceleration, it's the gradient of that velocity time graph. If you've got a curved line, you're going to need to draw a tangent before you can find that gradient. That will give you the instantaneous acceleration.